Hi, my name is Brenden. I'm here with Ash, Christine, Branden, Morgan, and Josh. We're going to be talking about our senior chemie design capstone, where we designed a paraxylene processing plant. During our presentation, we're going to be going over the general info of our project. We're going to be going over the products that we were going after and trying to produce. We're going to go through our designed process that we ended up coming with, our economics of that design process, and then our final recommendations.
The proposed plant design will be built in the Gulf Coast. It is designed to produce 4,400 pounds of paraxylene on an hourly basis. The proposed plant will be built in Texas in Houston. The existing site at this location needs to be renovated so that the paraxylene plant can be built. Facilities will need to be upgraded and updated. Leidy Chemical Companies also has facilities in Pennsylvania. There's a facility in University Park where research and development is conducted. Additionally, there's a small pilot plant in Philadelphia. The pilot plant in Philadelphia is near the Delaware River. Leidy Chemical Companies has this location so that it can leverage the resources of the Delaware River for shipping purposes.
As Morgan mentioned, we produce paraxylene in our plant. In order to do this, paraxylene is produced through a toluene disproportionation reaction, where toluene is fed into our reactor and paraxylene and benzene are produced. The mandated toluene feed for this plant design is 34,600 pounds per hour, and it has a 99.5 weight percent purity. One of the many challenges that we've encountered in designing this process is that paraxylene reconfigures into the isomers metaxylene and orthoxylene, and thus we've had the issue of trying to limit this reconfiguration. Another one of the challenges that we've encountered in the plant design is that paraxylene undergoes a disproportionation reaction to toluene and trimethylbenzene, toluene being our initial feed and trimethylbenzene being waste. One of the other features that's mandated in our plant design is that we must include a hydrogen feed in order to maintain reactor selectivities and prevent coking. In order to do this, we feed 1,700 pounds of hydrogen into the plant, which we will describe later why this number was chosen, and it is at a 90% weight purity. However, one of the drawbacks in feeding hydrogen to our reactor is that it can react with toluene in a toluene hydrodealkylation reaction, which produces benzene and methane, which are both wastes, and it therefore competes with paraxylene production. Our process is limited by feed conditions that are fixed, in that we can only have so much impurities in both our toluene and our hydrogen feeds. In our toluene feed, we meet all specifications in terms of these impurities. Additionally, in the hydrogen feed, we must feed it at a 2-to-1 molar ratio with the toluene feed, which our design accomplishes. However, within the reactor itself, our hydrogen must provide 250 psias of partial pressure, and we come very close to the specification at 247 psias. Some of the other many factors that factor into our goals and process design are market conditions that dictate the quality of products. We must achieve a certain purity with our product streams in order to be able to sell them for a profit. These include, in both the benzene and the paraxylene streams, forming the streams at a 99.9 weight percent purity minimum, which we accomplish, and only having so many impurities, which we also accomplish. And finally, our plant design has also been affected by mandated recovery conditions and waste limitations to ensure that our plant is operating adequately and efficiently. Unfortunately, we do not meet our design does not meet the specified recovery conditions of 0.85 moles of benzene and paraxylene per mole toluene feed. However, we do meet the specification that we can only lose 3% weight percent of our toluene feed at the end of the process.
Most of our components that we have in this process are skin irritants and eye irritants, and they're also harmful if swallowed or inhaled. During normal operations, our operators would have to wear personal protective equipment such as safety glasses, respiratory protection, safety gloves, and steel-toe boots. But during more extensive processes such as a line breaking or a cleaning of the plant, they would have to wear a hazmat suit to protect themselves. Another precaution that must be taken is that because our plant is run at high pressures and most of the components are either flammable or highly flammable, there needs to be control valves in the line and also pressure relief valves. Most of the components that are used in this process are hazardous to aquatic life. This is an important thing for us to consider because one of our plants is on the Gulf Coast and one of our other facilities is on the Delaware River. Knit Chemical Company strives to protect the environment, and we have implemented measures into our design so that we do not cause any environmental damages. We recommend to burn all of our waste in a chemical incinerator that includes an afterburner and a scrubber. And here is our overall plant design, which includes 3 main sections, including our reactor system, the removal of lights and recycle, and our purification system. And here's our reactor system, which includes the feeds of hydrogen and toluene, and also includes the removal of the lights, which are hydrogen and methane, and the recycle back into the reactor. Our purification process includes 5 distillation columns and a Peres absorption unit. The Peres absorption unit is used to purify paraxylene from the mixed xylenes. We also have a toluene product stream, and we have 2 separate benzene product streams due to our configuration.
The total contractor cost for the capital is estimated to be around $114 million. A large bulk of the cost comes from the purification processes from the Peres unit and distillation columns. There are 5 distillation columns, which is why it is 32% of the whole total capital cost. The Peres unit is the only separation unit that separates out the paraxylenes from the mixed xylenes. So even though it consists of 52% of the total cost, it is very much needed and cannot be removed or reduced out of the. The pressure changers consist 6% of the total capital estimate because the plant operates at a high pressure, which means that there is no need for a large pressure increase.
Hourly costs of materials to run the plant are $11,000. The most expensive component is the feed for the reactor. Other components to run the plant are catalyst, the licensing fees for the Peres, which are on a flow rate basis, as well as miscellaneous chemicals that must be added to allow the reactor to run smoothly and prevent coking. Sales of the proposed chemical plant are $10,000 per hour. The largest component is toluene, with over 56% of sales. Unfortunately, the desired products are paraxylene and benzene, which together are less than half of our sales. Toluene is over 56% of our sales per hour. This is due to the low conversion of toluene in the reactor. There must be a low conversion to prevent ortho and metaxylene from being produced. However, this is what leads to there being a large amount of toluene rather than paraxylene, which is our desired product in the plant. The operational cost of running the proposed plant is $20,000 per hour. The largest cost, at just over 52%, is labor. The second largest cost is utilities. The team designed the plant such that 2 of the heat exchangers use process streams to heat the other stream rather than using utilities. This saves on utility costs. Catalyst for this plant is purchased every 3 years. For the purposes of this chart, to show its relative magnitude compared to other purchasing costs, the catalyst price was divided over an hourly basis such that it was at a reasonable comparison.
The total cash costs are $1.58 per pound product with respect to xylene and benzene being our desired products. The raw materials account for 70% of our total cash costs due to purchasing them from outside vendors. The utilities account for 20% of the total cash cost. Within the utilities, refrigeration is the most expensive component. Due to the low product sales in comparison to the costs, the SG&A costs account for only 1% of the total cash costs. The fixed costs account for 9% of the total cash costs. The fixed costs include labor, insurance, repair and maintenance, and property tax. The plant design produces a negative cumulative cash flow and present worth. Throughout the duration of the plant's lifetime, the cumulative cash flow linearly decreases until the plant's conclusion. Due to the negative cumulative cash flow values, a rate of return could not be calculated, which also means a required netback to achieve this rate of return could not also be calculated.
Our current designed base case actually loses $976 per hour. So with that in mind and all of the negative numbers that Brenden calculated before, we wanted to end the project leaving with a few recommendations on how we would approach our next steps for this project. One of the topics that we found, one of the improvements that we found, was that we had a toluene product stream of 22,000 pounds per hour. We were purifying toluene outside of our reaction. We were purifying toluene past our reactor in our purification process so that we could sell off this large amount. However, if we take that 22,000 pounds per hour and recycle it back into the reactor, we hypothesize that we will get more paraxylene conversion, which is a more valuable product per weight compared to toluene. So with that improvement, we're expecting that our process would become a lot more feasible and it would be a lot more likely to be implemented. However, due to time constraints, we were not able to test this hypothesis and we weren't able to implement this process change into our project. Another improvement to our process design is if we can find a vendor that allows us to buy our toluene and hydrogen feedstock at 10% lower than we can sell our toluene, or 10% lower than we can sell our product chemicals. If we are able to achieve this and find a vendor who has agreed to do that, we would go from losing $965 per hour to actually gaining $660 per hour. Now those are relative numbers. That is before any sort of cost or labor it has been calculated in. Those numbers are purely just out minus in costs.
The current project definition rating index, or PDRI, score of the plant is 338. This is a normal score for a project at this phase of design. The PDRI score would be further lowered as the plant becomes more defined with piping charts and more definition within the process. At this phase, the team has already decreased the PDRI score from approximately 600 in the first phase of the project to approximately 450 in the second phase to what it is now at just over 300. As Brenden mentioned, the team does not recommend building the plant without significant process modifications at this time. Significant process modifications would include implementing a recycle for the toluene. As previously mentioned, currently the plant recovers a large amount of toluene that was not reacted within the reactor. It was important that the conversion in the reactor was low to prevent large amounts of side products being created. However, this did leave a large amount of toluene left over. The team would recommend that a simulation would be created for this toluene to be recycled. A recycle would reduce the feed costs, which is the largest contributing cost at this point. Additionally, the team would recommend optimizing the utilities in the plant. Utilities is another large cost for the team. When creating the simulation, the distillation columns and several other units were designed such that they ran to give the desired purities and met the hard specifications for the project. In moving forward with plant design, the team would recommend seeking to optimize these utilities to decrease costs operationally. Currently, only 2 of the heat exchangers have been optimized to use other process streams rather than utilities to save costs. Other heat exchangers could be investigated to save on utilities, among other things moving forward. Again, to reiterate, the team does not currently recommend building the plant as is. To conclude, the team would not recommend building the current designed plant as is. We would recommend implementing the proposed design changes to allow the plant to be profitable rather than lose money on an hourly basis.